parameter that we'll examine is the base resistance of a bipolar transistor. Unlike the MOS device that we'll look at in a moment, the bipolar transistor has a finite base resistance. We're going to look at a couple of variables in terms of both DC and small signal performance. So the first is the collector current. We're going to note collector current as little I big C, which is equal to the sum of the DC current through the collector plus the AC current through the collector. Now we know that our base current, IB, is equal to this AC collector current divided by beta forward. Substituting IC for the combined DC and AC term, we can write IC divided by beta forward, big IC divided by beta forward, plus little IC divided by beta forward. We can further note that little I, little c is equal to the transconductance, GM, times VBE. That's a little VBE, which is in turn equal to IC over VT times VBE. Substituting back in and just selecting the small signal term, that is the AC term only, we can write that little I, little b is equal to IC over beta forward VT times VBE. Now we define the base resistance, our pi, as equaling VBE divided by IB. So we can find that our pi is equal to beta forward over GM. Interestingly, this only depends upon the bias current and the temperature, as GM only depends on bias current and temperature. The next thing that we'll look at is the output resistance of the transistor, and I want to reiterate that these parameters are small signal parameters of the device. They're only relevant for small signal excursions, which is why we were looking only at this small signal base current and the small signal input voltage. Now in an ideal transistor, if we plot the characteristic curves IC versus VBE, we would get zero slope once we got into saturation for any of our characteristic curves. So this would be for a this plot should be versus BCE. This would be for VBE1, VBE2, and so on. We get zero slope, and if we have zero slope, no change in current versus some change in voltage, that means that we would have zero conductance at the output, or correspondingly infinite output resistance. In reality, when we draw these curves, there is some finite slope. And if we project that slope back to where it crosses the x-axis, the y, where the slope crosses the x-axis, we would find a point called the early voltage. And if we draw multiple curves for this transistor, every curve would project back to the same point. So the early voltage is a fundamental parameter of the device. Now, if we find the slope of this curve, now we see that there is some slope. It's not zero any longer. And the slope is proportional to 1 over the output resistance, R sub 0. So we measure our slope as equal to IC divided by the early voltage minus VCE at any point. And this is equal to G sub 0, which is the output conductance. We can invert that to find the output resistance. Now, we desire to have VA to be very, very large, and that would make our early voltage, that would make our output resistance very, very large. So, before we noted that our expression for current in the bipolar transistor was equal to IS times E to the VBE over VT. Here we have to note that we can modify it in the face of output resistance by adding this 1 plus VCE divided by VA term. And again, if VA is large, then it has very little impact on the output, on the current expression. So, with all of this in mind, we can arrive at a small signal model. And again, this is only valid for small AC swings around a DC bias point. So we know that our GM, our transconductance, is equal to IC over VT. This is how well the transistor converts voltage at the input base to emitter to a collector current through the output. Our output resistance is equal to IC divided by VA, inverse of this. And this is approximate. Remember, it would technically be IC divided by VA minus VCE, but we assume that VA is very, very much larger than VCE. Finally, we have our pi, our base resistance, which is equal to beta over GM. It's also equal to our thermal voltage VT divided by our base current, just an alternate expression for it. So our small signal model starts at the gate terminal. We have the depletion capacitance. This was called C pi. I'm sorry, this is not the gate, this is the base. We're not looking at MOS devices yet. So we have the depletion capacitance that goes between the base and the emitter terminal. We have the base resistance, R pi, which goes between the base and the emitter terminal. We have a voltage-dependent current source, GM times VBE, where we know VBE is the potential difference between the base and the emitter. We have a capacitance between the base and the collector. This one was C mu. This is the depletion capacitance from the base to collector junction. And finally, we have an output resistance that goes between the collector and the emitter. If we were to try and find a voltage gain for this transistor, if we tried to find the voltage at the collector due to a voltage input at the base, we would find that the intrinsic gain of this device is equal to GM times R sub 0. Any circuitry that we add to this transistor can only reduce the gain from this number. We'll look at the MOS small signal model next in lecture 2.